All right, we're going to do lesson 4.2, linear rate of change. I want to talk about one of my favorite examples that I use whenever I talk about solving math problems, and that's how we're going to the store. Sometimes I recommend that you go to the store on a bicycle, right? Let me see. Let me make sure I get my frame right. Got my down tube. Got my fork. Saddle. All right. That's kind of a bicycle. It's close enough. Okay. Actually, it should be something like that. Anyway, you're on your bicycle. We're trying to get to the store, the happiness store. And you hop on your bicycle, and you're able to, the store, let us say, is 10 miles away. 10 miles away. And it takes you 1 hour to get there. It takes you 1 hour to get there. Does that make sense? Is that easy enough? Now, conversely, what you could do, so you could use a different vehicle. Which vehicle would you like to use? You can use it in your rocket ship. And here's your little window. Okay. We're going to go to our rocket ship. We are still, well, maybe we're not going to go to the store. Maybe we're going to go to like Mars store. Okay, we're going to the Mars store. I have no idea how far away Mars is. Does anyone know off the top of their head? We will go 100 miles. We'll say it is 1,000 miles away, which is not true at all. Not true at all. 1,000 miles away is like maybe, what is like 1,000 miles away? San Francisco is probably about 1,000 miles away. Okay. So maybe it's not Mars, maybe it's San Francisco in your rocket ship. It takes you exactly 3 hours to get there. Okay? We will say. Now, what we need to be able to do is, I would ask you a question. After seeing all this, I would say, which has the highest, I might say something like rate of change. And the question is, what do I mean when I say rate of change? What is rate of change when we're talking about it in this regard? Well, in this case, what we're going to be talking about rate of change is we're talking about speed. We're talking about how fast something moves, right? If you have the bicycle and you're riding it, it's changing. You are going forward at a certain rate. However, if you go on the rocket ship, you are going forward as well as a certain rate, but which one's going to have the higher rate? Which one's going to be the fastest change? Clearly it's going to be the bicycle. No, clearly it's going to be the rocket. Okay? And we can figure this out mathematically, because these are like two very divergent things. Like a bicycle versus a rocket ship. We know one is going to be much faster than the other. But we could also figure it out mathematically, because when I talk about rate of change, one of the things that I'm really talking about is slope. I'm talking about m. Because when I talk about m, I'm talking about rise over run, yada, yada, yada. But I'm talking about the change, the delta of y over the delta of x. And we all know that delta means change, because I keep saying it every time I write delta. And we all know that little triangle is a delta. Okay? The change of y over the change in x, that is our rate of change. This is all the same vocabulary, or different vocabulary for the same concept. And so we can easily figure that out. My change in y is 10 miles over 1 hour. So I could say that my slope here, well, it's 10 over 1. My rate for my bicycle is 10. I'll move it over. My rate for my bicycle is 10. And so what would my rate for my rocket ship be? Well, it's 1,000 over 3. So it's 1,000 thirds. Or if I were to get it into a little bit easier to understand form, 333.3 bar. Okay? So my slope is 333 compared to 10. Which is the higher slope? Clearly this is a larger number than 10, thus it has a higher rate of change. Does that make sense? Now let's talk. Now one of the things I'm going to ask you guys to do is I'm going to ask you guys to convert between units. All right. So I'm going to ask you to do something different. Let's say, Carol, who's the worst driver that you know? Like drives fast, recklessly. One of your sisters? Okay. So let's say, I'll call her sister. We don't have to out her. Reckless driver. Going to the store. You know, it's 10 miles. Takes her an hour. Bob is a guy I know. Same 10 miles. He gets there in 24 minutes. Okay? Rate of change. Okay? So here, clearly we know that 24 minutes is less than an hour. That's going to be the faster rate of change. But how much faster? To what degree faster is that? And to be able to do that, we need to convert our units. Now we can either convert units to, or hours to minutes, or we can convert minutes to hours. It doesn't really matter as long as we're consistent. Because if I were just to compare these, this would be 10 over 1, this would be 10 over 24, but we're comparing hours and minutes here. We're not comparing like and like. So this relationship doesn't make sense. Yeah? You could, absolutely. That's a very easy way of doing it. So instead of 1 hour, I would say 60 minutes. Yes? Yeah, the miles are still the same. Now, if I had instead said, like, okay, instead of going 10 miles in 24 minutes, he's able to go, I don't know, 3,000 yards. Well, then we have to convert yards to miles or miles to yards to be able to compare their rates. Okay? But I'm just keeping it simple for now. We'll keep it at 10 miles, just so that we're only comparing one. Okay? So suddenly this isn't 10 over 1. Instead, it's 10 over 60 compared to 10 over 24. When we reduce those down, 10 divided by 60 becomes 0.16 bar. 10 divided by 24 becomes 0.416 bar. And we can clearly see that 0.4 is higher than 0.1. Therefore, we know that this is the higher rate. Now, we knew this intuitively, right? We knew that getting someplace in 24 minutes is going to be faster than getting someplace in 60 minutes. But this is just showing the mathematical relationship to what we already know. We see that our slope is a higher number than the other one. Thus, the higher slope, the greater slope, shows that it is a faster rate of change. Now, what does that look like when we graph it? Okay, where's my protractor? Okay, so here's what I'm going to do here. So I'm going to say, this is 10 minutes, 20, 30, 40, 50, 60, okay? And then let's say this is 1, 2, 3, 4, 5 miles, 6, 7, 8, 9, 10. This is in miles. This is in minutes. Okay? So, Carol's sister goes 10 miles in an hour. Okay? So after 60 minutes, she's gone 10 miles. Looks something like that. We can assume she keeps driving, so I'll put an arrowhead on the top of it. My buddy Bob will go 10 miles in 24 minutes. Well, 24 is about here, and then you go to 10. Okay. And so what we see is, what's the difference between the green line and the red line? What are their slopes like? What do they look like? Gracie? Yeah, it's steeper. Steep. It's shooting up at a higher rate. So we can see that this green line has a higher rate. It is faster. Does that make sense? So that's how we visually understand this mathematical relationship and this other relationship that we just intuitively know. If I were to give you, with no context whatsoever, a similar sort of graph, okay, so I'll say this is minutes, this is miles, okay, and I have one line going like this, and I have another line, maybe they start later, going like this. Which vehicle or person or anything is going faster, the green or the red? The red. The red is going faster. Even if the green has traveled further at any given point, right? If I were to just stop at this point here, if I were to say maybe this was 1 minute, and I were to stop there, I'd say, oh, well, green's gone farther than red. Green's going faster, right? No. The red still has the higher slope. The red is the one that's going faster. Like, are you guys ever driving and you're at a stoplight? Okay. This is like a 4-way intersection. Okay. You're stopped here. And then the light turns green, right? The light turns green, and you go from 0, and it takes you a while to accelerate, and eventually you get moving. But there's a car right next to you who never had to stop. They happen to get to the light right when it turned green, and so they blow past you. You guys ever experienced that? They just go zoom, or maybe you're the car going zoom, like everyone else has stopped, and you're like, I can time it just right, boom, and you hit it. Same sort of concept. This car is going faster. Even if they're at the same place at the same time, that one is going faster. Questions? Intuitive concepts. It's just trying to convert these ideas into understanding how they relate mathematically. Okay? The things that I want you to get out of this is understanding, one, that the greater slope means the greater rate of change, which means it's moving faster. And 2, the steeper slope is the greater rate of change, is the higher slope, thus it's moving faster. Questions, comments, criticisms? Whoops. All right, I'm going to stop the video.